Hi there, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and this video is going to focus on radio galaxies and how we classify them, because we can split them into two main types. So this video we're going to kind of recap what galaxies are, have a look at radio galaxies, and then how we might actually classify those into kind of radio loud or radio quiet. So just to recap on galaxies, this is kind of what I'm doing on most of my galaxy videos now, just in case you're not familiar with galaxies at this point. If you are, you kind of go a bit forward into the video and go straight into the radio galaxy part. So galaxies are these enormous structures of stars, gas, dust, dark matter, and they're generally gravitationally bound to one another. Not to one another, I should say. They're gravitationally bound. So some of them are kind of rotating, some of them are more spherical like. They have different amounts of stars, gas, dust and all that in them depending on their actual type, and there's a whole range of different types, shapes, sizes, things like that. So just to give you an idea here, they come in a huge variety of sizes and shapes depending on kind of where they are evolution wise, what they're made of, how they've interacted with other galaxies. So they could be more disc-like, they could be more spherical, they could be, kind of rotating, have old stars, new stars. But anyway, whole variety of different shapes and sizes, but they're predominantly made of or composed of stars, gas, dust, obviously significant amounts of dark matter as well. So if we go to the different sorts of galaxies and we look at the Hubble galaxy classification system, we typically see this kind of tuning fork diagram. There can be kind of three forks on the right hand side, but most of the time we're more interested in kind of the normal spirals and the barred spirals. You can have intermediate one, and they sit on the right hand side. They're your spiral galaxies. They're more disc-like, so they have a net rotation. They kind of the stars or the disc plane is rotating in a common direction. As you kind of go from right to left, they get older, so they actually evolve from right to left. Spiral arms get a bit more tightly wound. Their gas content is depleted as it's transformed into stars. Maybe transformed is not the right word, but the gas forms into stars. The stars get older, so they kind of get redder as well. And then if you go a bit further over, you've got your elliptical galaxies. These are classified purely by shape. So these don't have spiral arms. They're a bit smoother in appearance. They can be a bit more symmetrical. And these have older stars in. They have very little gas content, if any. And these are thought to be older than your spirals. And they are kind of a natural end point to the spiral galaxy evolutionary process, I suppose. They can get there in a few different ways. Again, different videos on those particular ones, but these are classified by shape, whereas the spirals are classified by their shape, also what they're comprised of as well. So if they've got older stars or younger stars, then we classify them on that. I'm missing out the lenticulars and the ones in between because they're a little bit more complex to discuss, but they sit in between the spirals and the ellipticals. So some of these galaxies, and this goes for all types of galaxies actually, so ellipticals, your spirals, some of these have these active supermassive black holes in the center, and we call those AGNs, so active galactic nuclei. So some of these galaxies are essentially active, and I've zoomed in a bit here. So the very first not zoomed in section, the first yellow box is the optical image of the galaxy. And zoom in, you can see that's what it would look like if we kind of looked with our eyes in the optical part of the spectrum. And going a little bit further, and you've got this active black hole that's essentially feeding, so it's accreting matter onto itself from a disk. And then you've got these jets, and then that produces these massive radio jets. So anyway, some galaxies are active because they have these feeding black holes at their center. So they're going to be powered by the supermassive black hole. So at the center there, you've got a supermassive black hole, and these can be billions of solar masses. So these are significantly massive black holes. And what typically happens with these when they're active is you have this hot accretion disk, and it is gradually falling onto the black hole, and that's what powers them basically. And also, I'm not going to go into it in detail with this video, But when we look at the electromagnetic spectrum given off by one of these active galactic nuclei, this hot accretion disk accounts for some of the emission that we see. The closer it is to the black hole, the hotter it's going to be. So we get kind of like a full spectrum, really. And when that material is falling onto the supermassive black hole, you then get these high energy jets emitted perpendicular to the disk. So these very high energy relativistic jets are perpendicular to this disk. And this is very important for what we're going to discuss about the radio galaxies, basically. And if we zoom out from the galaxy, we get this sort of structure. So in the yellow square here, we've got the optical or the main galaxy where the stars are, the gases and things like that. But then those jets that are being emitted from the supermassive black hole due to its active nature, these can be hundreds of thousands of light years long, basically, and they can be significantly bigger than the galaxy themselves. So the radio jets that are emitted can be much, much bigger than the galaxy that these supermassive black holes are residing in. So this one not so much, but we've got our radio jets there coming perpendicular to the actual plane of the galaxy. So we're kind of looking edge on at this galaxy here. And the center part where the yellow arrow is, that's in the optical part of the spectrum. And then the jets perpendicular are taking the radio part of the spectrum. So this is like a composite image, including the radio emission and the optical emission. So we can, now that we've got these active black holes in the center and we've got these radio jets or these lobes being emitted, we can classify them as radio loud or radio quiet. Well, actually, I should say the radio quiet aren't going to have those radio jets. So we've still got these active black holes. Some are going to have these large radio lobes and some aren't. So we've got radio loud, radio quiet. Now the one I'm going to focus on here really is mostly your radio loud, because your radio quiet doesn't have those large scale jets. And we're then going to classify the radio loud into two types, the FR1 and FR2. Radio quiet, we'll do a separate video on those because they're kind of like your CFER galaxies instead. They still have the active core, but they just don't have those big jets. So if we look at the full electromagnetic spectrum of these active galactic nuclei, these active galaxies, we get something that looks like this. It looks quite complex, but don't worry about it. If we look at the radio part of the spectrum towards the left, so it goes from radio all the way up to gamma ray, and I've highlighted your radio loud and your radio quiet. So the radio loud are very energetic in the radio part of the spectrum. They have like an excess of radio emission compared to your radio quiet. So the radio quiet, they're not really emitting much in the radio part of the spectrum. Radio loud, significant amounts of radio emission is being emitted there. Now, it's worth noting that actually, if you've got a radio loud or a radio quiet galaxy, they're going to share similar emission from the central part, from the actual active black hole in the center part. That's from the accretion disk and all of essentially what's going off in it, in and around that, and depending what angle you're looking at. So there could be like a dusty torus. You're going to get reflections off that from the accretion disk, and that's where a lot of this kind of broad emission comes from there. And the difference between the radio loud and the radio quiet is just in the radio part of the spectrum. One is more energetic than the other. So now we've got our radio loud galaxies. How are we going to classify those? Well, we can classify them using the FR system, and this will put them as FR1 or FR2, and it classifies them in terms of their brightness and their structure. So at the top there in the yellow box, that's an FR1, the bottom one is an FR2, and we'll explain what that brightness and structure is and how we actually get the different classifications really. So it just depends really on the distribution of your radio emission relative to the core. So the core will be the center part, the supermassive black hole in the center where all the activity is going off. You've then got the jets being emitted, and the classification depends on how that radio emission is distributed along those lobes, those jets, relative to the core. Some of it might make sense actually. It's not too difficult to kind of understand. Now, there isn't really a proper like a mathematical way of doing it, but we can look at the morphological ratio R here. And what it's going to do is it's going to look at the distance between the brightest points on opposite sides of the central core divided by the total distance between the outermost edges of the radio lobe. So it's going to be a ratio of where the brightest part in the lobe is relative to the outer part. So is it towards the edge? Is it closer to the core? And it gives us this ratio R really, and that can help us classify between the two. So just to give you an idea there, at the bottom one, the brightest part is actually quite close to the outer part of the edge. So you've got the lowercase d and then the uppercase d. If we were to look at the top one, FR1, you might see that it's actually brighter emission towards the core. So the top number would be less and you'd get a lower R number. So if your ratio between the brightest part and the outer part is less than half, it would be classified as the first type, FR1 essentially. And that's an example of one there. The brighter parts are actually closer to the central core as opposed to being in the outer parts of the lobes. And then what we've basically got is we've got our ratio being greater than a half. So if it's more than 0.5, it's going to be classified as FR2, and you can see an example of one here. The brightest parts of the radio emission is stronger, brighter at the outer parts of its lobes. That will be classified as an FR2. So some key features then between the two types. So for the first type, the FR1, the brightest emission is going to be near the core, and then it fades as it goes outward. Again, we could see that from the images and from the data there. The actual jets themselves are going to be quite broad, diffuse, and nearer the core they can actually be quite turbulent as well. So they're not quite as maybe focused as the other one. And then the lobes on them are going to be quite faint, more symmetrical than the FR2 types. So the lobes are going to be at your outer part, which we kind of know because the brightest parts are towards the core. Now with the FR2, the brightest emission is at the outer edges. Again, that's why we've got this type here, this classification. The jets are going to stay quite narrow and focused over very long distances, and you then get kind of the brightest emission at the very edge. And the lobes are going to be very large at this point. They're well defined and also asymmetric as well. So key features between the two types. Now, where do we typically find these? Well, the first type, the type that's got the brightest part towards the core, the FR1, these are typically found in low luminosity sources, and they're typically also in dense environments like galaxy clusters. So the galaxy itself might be in a galaxy cluster, and it might be quite a low luminosity galaxy as well. And you can see here, again, this graph doesn't make a huge amount of sense if you don't understand it. Lots of different sorts of galaxies here, which I'll do some separate videos on probably. But the FR1 sits lower down on your energy than your FR2, so it's a low luminosity source, typically in dense environments like galaxy clusters. And then our FR2, typically high luminosity sources, and these are going to be significantly more powerful than your FR1, which again kind of makes intuitive sense when we think about the actual structure of the jets and the lobes as well. And then just a couple of examples really of each type. So this one here is NGC 4261, bit of a mouthful, but this is an FR1 radio galaxy. So what you've got here is you've got the Hubble Space Telescope image of the gas and dust disk in this galaxy in the center, and then you've got combined the optical and radio image on a much wider image there on the left hand side. So again, you can see the brightest parts are probably not towards the outer edge, and it likely is less than 0.5 on your ratio. And then Cygnus A is a pretty good example of the second type of radio galaxy. And you can see you've got significant jets coming out, quite narrow to a point, and then you've got these very large lobes which are brighter than the actual parts closest to the galaxy. So thank you for watching, and if you enjoy the videos or find them helpful, then do consider becoming a member of the channel. There's extra videos in the member section, and it just generally helps support the channel. So thank you for watching.